In this lesson, I'm going to talk to you about how to handle missing data. Oftentimes, we find ourselves working with data that does not record every variable for every observation. When data is missing, we may need to use different fixes before we begin running different analysis. When data is loaded into R, it will deal with missing data in a couple of different ways. So accompanying the video should be a text file called weights. You should put it in your working directory, and when you open it up, you'll see this. It's going to be a data file containing information for weight, height, and gender for 5 different people. Now let's use our read.table function to load in this text file and see how it behaves. We'll make sure to set our header to equal true so that it knows that there are variable names. And we're going to use the separation argument. And we're going to set it to be a period. So that's how it knows how to separate the data. For missing numerics, such as the second person has no recorded weight, it will replace it with a NA, which stands for not available. For missing strings, it fills the spot in with a blank. Now we can test for these missing values using a simple function called is.na. So why don't we reload this data and assign it to a variable. And now we can use the is.na function on the dataset. And it will return a true or false for every element of that matrix, whether it's a NA or not. For gender, you'll notice that the blank, the missing observation, will still be false because it's not an NA, it just happens to be missing. If we want to look at a specific row and column, we can throw that in directly after data using the square bracket subsetting. Now we can also set values to equal NA if we want to ignore it. So let's say that the height for the first person is incorrect. Currently it's 72 inches. We can easily set that to NA like this. And now there's an NA in place where it was originally 72 inches. Now let's see how a simple function behaves when there is an NA in our data object. Let's try the mean of the height column. This returns NA because there's an NA in that column and it doesn't really know how to deal with that. We can fix this by using the na.omit function. So I'm going to wrap that height variable inside of the na.omit function. And now the mean function works just fine. And we can pull this out so you can see exactly what it looks like. So now it's just giving us the 3 numeric observations and leaving out the 2 NAs, the one that's at the start and at the end. You can also throw this directly into the function as an argument called na.rm. So let's try this again. And now let's throw in the na.rm argument. So you can think of that as na remove. And it produces with a numeric answer. Now, if we use na.omit on the entire data set, it's actually going to remove whole rows of data. You'll notice that it removed the first, second, and fifth rows as those had NA observations. Now, a similar function is called complete.cases, which will tell us which rows have 0 NAs. So here it will return a Boolean vector that is as long as there are rows in the data set. It's telling us that the first 2 are not complete because there are NAs. Same with the 5th row. And we can create another data set called complete data using this information as a subset. We received an error because I didn't use a comma to specify that I'm trying to return just the complete rows. Another NA function which is very helpful comes from the XTS package, which is called na.locf. I'm going to quickly create some fake price data for 2 different companies. Company X, which is going to equal a cumulative series of random numbers. And then a second company, Company Y, which is going to equal the same thing. But because of random numbers, we should get different results. Now we can plot both series. And we'll set up a layout. File margins are too large, so I'm going to expand my plot window a little bit. And I forgot to put quotes around my plot type, so it didn't really recognize it. So here are the 2 different companies, and you can see that they look kind of similar. So now why don't we try throwing some NAs in the different company price series? and we'll see how we can deal with this. So I'm going to make the prices of the first company for 10 different rows to equal NA. And then for the second company, company Y, I'll do that again, but I'll do even more, around 20. So now let's plot these again and see what they look like. You can see that they're just missing chunks. It doesn't know what to do with the NAs, so it just omits them completely. So now let's try using the na.locf function, which carries forward the last observation through a series of NAs. So I'm going to do it to the whole price series. First, we need to make sure we load our XTS package using the require function. And now it works just fine. Let's plot these again and see how it behaved. So now it should be kind of clear what this function does. Where there was originally a gap, it now just took the last numeric observation and carried it forward through the whole group of NAs. Now there's also a function called na.fill, which allows us to specify how to fill the NAs. So why don't we go back and put those NAs back where we originally placed them. Now we're going to try the na.fill function. And we need to specify a new argument, and this one is called fill. The example I'm going to show you is going to be the extend method. Now, when I use the na.fill function on my price data, it actually turned them into atomic vectors, which is basically just a numeric data matrix. It no longer is a data frame, so we can't use that dollar operator anymore. So instead, I'm just going to specify the column number. So what na.fill does is it actually works in a step function, slowly incrementing from the last good observation to the next good observation. So you'll see it shows up as a diagonal line. Now sometimes missing information comes in the form of NaN, which means not a number. For example, if we divide 0 by 0, it's going to say NaN. It's not a number. A function that is useful for pulling out NaNs is is.nan. And if we throw 0 divided by 0 in there, it will come out with true. And a couple other special numerics include both positive and negative infinite numbers. For example, 20 divided by 0 is infinite. Negative 20 divided by 0 is negative infinite. And there are two other functions, is.infinite. It returns a false because I divided by 1 instead of 0. If I put 0, it's going to return true. These special numeric functions can help you figure out why different functions may not be working, or why they return an infinite number. In this lesson, I gave you an introduction on how to handle missing information. There are many different methods, and hopefully you'll find them very helpful. In this lesson, we're going to talk about how to order and sort your data. So let's open a new data set using the data function. I'm looking for a data set called petrol, which contains information about different barrels of oil. So the mass package wasn't loaded, so let's try and load our data sets again and see if it's there. Here we go, petrol. We can load it using petrol, the name of the data set of interest, as an argument in the data function. So it's 32 observations of 6 different variables. But we're not really sure what those column headers mean. So we can get some more information about the data set by using the question mark right before the name of the data set. So this data set is called Prater's Petrol Refinery Data, and we can see what the different columns mean. So let's rename the columns for some more clarity. I'm going to use the names function of the petrol data set. I'm going to rename them a vector of character strings. So I'll start with ID, spec grav for specific gravity, vapor pressure, vol crude for volatility, vol gas for volatility of gasoline, and percent crude, which is yield as a percentage of crude. Now, currently the data is ordered by sample ID, but we can use the order function to switch it around. So let's say we want to get the order of vapor pressure. The order function gives us a vector of numbers relating to the row. We can use this in bracket subsetting to rearrange the data frame. So now I'm going to put this inside of some square brackets. I'm going to make sure to tell it that I want to order the rows and not the columns by putting it to the left of the comma. It's now ordered vapor pressure, starting with the lowest and ending with the highest. Now, if we want it to decrease instead of increase, we can set an argument inside the order function decreasing to equal true. And so now we have the reverse data set. Now, each vapor pressure is repeated 3 times for each sample ID, so how can we sort it even further? Well, inside the order function, we can actually set it to order by multiple variables. So after vapor pressure, why don't we order by the volatility of gas? This code is going to order the dataset first by vapor pressure and secondly by the volatility of the gasoline. I'm going to create a new petrol dataset ordered by the yield as a percentage of crude, and I wanted to do it in a decreasing fashion. Now there's also an argument called na.last, which is a logical argument that tells the function where to place the NAs. For example, I'm going to go back to my old dataset, petrol, and I'm going to change some of the percent crudes to be NA. Why don't we do the first 10? And then when I order my dataset by the percent crude, and we can set na.last to equal true. And this will just put all the observations that come out as NA for that variable at the bottom. Now we may also want to reorder the columns. One way to do this would be to use our new dataset, and we can use the order function on the names of the original dataset. And what this is going to do is it's going to alphabetize the names. And it didn't work because my new data object is not called new data. It's actually new petrol. And here it's now ordering the columns in alphabetical order. So in this lesson, I talked a little bit about the order function and how you can use it to organize your data. You can also order multiple variables at once, giving more importance to one over the other. In this lesson, we'll cover how to create new data sets out of subsets and indexing. There are a few different ways to exclude variables and make subsets using both negative signs and explanation points. Before we get started, let's make sure to load some data, and we're going to take it from the mass package. The data of interest is the Cars 93 data set. We can quickly explore it using the head function. We can see that there are a lot of variables, 93 observations with 27 different variables. We could have also done this by using the dimension function. Now let's first look at the familiar square bracket subsetting. So I'm going to take out just a few columns. We're going to look at the model, type, and price. So executing this just pulled out those 3 columns, and I could have assigned this to a separate subset data of this full data set. Instead of putting the column names, we also could have just entered in integers specifying the index of that column. We can also use the which function. This is a logical function which returns matching values that cause the statement to be true. For example, let's look at the Cars 93 dataset, and we're going to ask which column names of that dataset equals the string model. And it returns the full list of models. Now, why don't we just look at that which function to see how it behaved? So it returns to us just a single number, and that number is the column index that we're interested in. Now let's look at some other helpful ways to use the which function. I find it to be extremely helpful for subsetting rows because we can easily extract a single characteristic. For extracting rows, we need to bring the which statement to the other side of the comma. And why don't we search for a specific cylinder type? This line of code is basically saying that I want the rows for which the cylinder column has a rotary value. And it's a little messy, but you can see that there's just one car, and it's the 57th observation of the Cars 93 dataset. It's a Mazda XR7. What about cars with 8 cylinders? Well, there's a few more. It looks like there are 7 observations that are 8-cylinder engines. Now we can subset by rows and columns simultaneously. Right now we're pulling out all the rows where the cars have 8 cylinders. But maybe we just want to see the model and price of those cars. All of these cars have 8 cylinders, and these are the different prices in thousands of dollars. What about for a 6-cylinder engine? Well, there are many more 6-cylinder engines. Now this can be helpful because we can compare the means of these different groups. So I'm going to wrap this subset data into the mean function. It returned an NA because I'm trying to get the mean of model names. Instead, I just want the mean of the prices. So I'm going to take out the model column. We can see $24,000. And then for an 8-cylinder engine, it's $33,000. So a little more expensive. Now let's create a subset of the car's data set, and we'll call it Ford data. This is going to be the data for all the Ford cars. And instead of getting the full 27 variables, let's just pick out a few that we might be interested in. We'll get model, price, miles per gallon in the city, whether they have airbags, and number of cylinders. And so this is the data set, and there are 8 different cars produced by Ford in 1993. Now we can use a negative sign or an exclamation point to exclude certain data. So let's say we want to exclude cars with 6 or 8 cylinders. So we'll use our Ford data set. We're going to use minus which. So this line of code removed all of the cars that have 6 cylinders. In this lesson, we talked about how to subset and index your data and how to create new data sets that might contain specific information from the full data set. The most important function to take away from this lesson is the which function. In this lesson, we will be discussing the merge function. We are already familiar with C binding and R binding. When we have 2 data sets and they share certain attributes, we may want to merge them to make one data set. When we do this, we can tell R how to handle missing data, whether to remove them or fill them in with an estimate. The merge function works on data frames. So first, I've created a couple data frames ahead of time. And you can see that there's some city information and some weather information. So I'm going to source this short file. So first, let's look at our city data and then our weather data. So there are a couple things to point out. First, what the heck is the I function? You can see it right here, and you may not have noticed it when we first started the lesson. Now, the I function will stop R from converting strings to factors, keeping them as strings. This is very similar to setting strings as factors to false. So we have 2 data sets, and some of the information lines up, such as city name. But there are different cities in both data sets. Let's discuss match first. This function takes a vector and compares it against another vector, returning all of the index numbers for where matches occur. Let's look at the city column of city and places column of weather. So if I pull out city, $city, give me all the city names, and weather, $city will give me the city names. So I can use the match function to see which ones match. So we're going to match the city, cities to the weather, cities. And we get index numbers. If we want to extract the values, we can subset. So I'm going to put this match function inside of some square brackets, and then we're going to have it return the weather city locations that match the city locations in the city data set. Now the city column could have other cities that don't match any of the weather locations, and those would also be excluded. There's also an operator that works just like the match function called %in. So it is a % sign followed by the word in and closed off with another % sign. So what this is telling us is that each observation in the city data set is in the weather data set. Now, if we do it the other way around, it's going to be a longer vector of Booleans, and some of them are going to be false, because we know that the number of cities in the weather data set is longer. Now, how can we merge these matching tags into one data set? Let's try using the merge function. We're going to merge the city data set with the weather data set, and we're going to set by.x to equal city and by.y to also equal city. And there we go, a new data set with combined cases. I told the data frame to merge the datasets by the column names that include the locations. It then removes the names which are not in both vectors. For example, city is the X data frame and weather is the Y data frame. So when I set the argument by.x, I'm telling it which variable to match with this variable from the Y data frame, which is weather. Now, what would happen if we didn't specify by.x and by.y? Well, it still works because we happen to have two columns that share the same name. Whenever a variable in one dataset matches a variable in another dataset, it automatically merges based on those two. Now let's change the city name in the weather dataset to be places. Let's rerun this code. Now what do you think will happen when I try to merge the two datasets without specifying which columns? At this point, they don't share any of the column names. It behaves by making all possible combinations of the city data with the weather data. So the city data contains 5 rows, while the weather data contains 8. And when we merge the two without specifying by X and by Y, when they don't share column names, it creates a dataset with 40 rows. In this lesson, we talked about how to merge datasets, and you can see that it's kind of tricky. But some very useful points that came from this lesson are the in operator and the matching function. Now let's talk about how to examine data and files. There's a group of helpful functions that characterize data, files, and objects. For example, we may often want to check to see that a file exists before we try to load it, and we may also want to know the file size. Let's take a look at the Files tab, and we'll use some of these functions. Now the first function, file.exists, will tell us whether the file exists or not. We can enter just the file name to look for something that is in the current working directory, or we can write a file path if it exists somewhere else or doesn't exist. So we need to use quotes around the file name, and for example, I'm going to use 0402 underscore list.r. It returns true, and we can see that it's right here. If I make a spelling error, it's going to say false. Now this is very helpful when loading data in an iterative manner. If the file does not exist, we can simply set the script to skip it and move to the next file. Now we can delete a file in R using file.remove, or we can rename a file using file.rename. The first argument for file.rename is the current file name, and the second one is what we want to change it to. So I'll just add an extra S. It says true, telling us that it worked properly. And now you can see it down here, lists with 2 S's. Now we can create an empty file if we need a placeholder using file.create. And I'm going to create one called empty.csv. And let's sort this Files tab by modified. And you can see that there is now an empty.csv, which is 0 bytes. So there's really no information there. Now we can also get a list of all files and folders that exist within a folder. If you execute list.files with no path, it's just going to return all of the files that are in your current working directory. Another powerful tool is file.info, which returns a series of attributes about that file. So let's try to get some file information about the empty CSV object we just created. Now returns size, which is 0, isdir, which is asking if it's a directory or not, among some other things. Now we can extract the size using the $ notation and using the size name. And it returns 0 because we know it's 0 bytes. Now we can use these functions for any file on our machine. When we search for a file name, it automatically looks in the working directory. To get a file in a different folder than the working directory, you need to add a full path. So what about objects in the R environment? How can we characterize those? Well, object.size will tell us how big an object is in bytes. So let's create a simple object and use the object.size function on that object. 88 bytes, so very small. Now, when processing data using R, it is helpful to process smaller objects. Now, to get the size of all objects in the workspace, we can embed the ls function inside of the object size function. So I'm going to create a few more objects very quickly. We can see what the size of all our objects are. So if we do object size on Y, we're going to see it's bigger, and then Z is going to be even bigger. But if we put ls into the middle of the object.size function, It actually just gives you the object size for the list of objects. So 216 bytes is how big this small list of objects is. In this lesson, I gave you an introduction to how to evaluate files and data on your computer, but also in your R environment. This can be very helpful. In this lesson, we're going to begin learning how to dissect data and look for interesting information. We have now built up enough tools and ideas about data types that will help us quickly build a path for uncovering information. At this point, we'll start revisiting many of the functions that were introduced in earlier lessons. So let's start by loading a famous dataset in R from the datasets package. So I'm going to make sure to load my datasets package. And of course, you know that if you do not have it, you can use the install.packages function to download the packaged datasets. Then I'm going to use the data function to load the iris dataset. So let's look at just the first few rows of iris. So this dataset describes different flowers and their sepal and petal lengths. The sepal is the green leaf that usually resides directly underneath the petals. It also gives the iris species of each observation. This data is generally used to teach classification methods to predict what species a flower is when you know its petal and sepal information. First, let's use the summary function to get a little more information about each variable. So we can see that there are 3 different species we're working with here: Setosa, versicolor, and virginica. We can get the dimensions and the names, and we can check to see if there's any missing information. So I'm asking, are there any NAs in the iris dataset? And it's false. They are all complete cases. So let's break it up by species and see how different the results are. So I'm going to create a new dataset called iris split. And there's a function called split that will split up a dataset based on a certain variable. So I'm going to split up the iris dataset based on the species. Our iris split dataset is now a list containing 3 different components. Now let's summarize the different pieces. When we summarize each one, you'll notice under the species variable on the right that there are 50 observations for each one. We can see that the means are a little bit different for each one. It gives us a lot of information, but it's kind of hard to see it. Ahead of time, I've prepared a little bit of code to plot some of this information. So let me walk you through the code real quick. We're going to be plotting the petal lengths against the petal widths. And for our color argument, I'm going to use an if-else statement. So it's going to color each observation based on what its species is. For example, if the species is Setosa, we're going to color that dot blue. If that's not true, then here's the false part of that first if-else statement. If the species is not Setosa, and if the species is virginica, we're going to color it red. Otherwise, all observations, we're just going to color green. So this is your first introduction to the if-else statement, and we're going to have a more in-depth talk about it later on. Lastly, after the plot runs, we'll run that right now, I'm also going to be adding a legend using the legend function. It's going to be placed in the top left. I'm going to be using the different species names along with the colors that I've assigned them. Even though the summary of each individual species was kind of hard to decipher just looking at the numbers, when we plot the information, we can see that there is a very distinct pattern. Every iris that is a Setosa tends to have a smaller petal width and length compared to the other 2, while virginica and versicolor get a little mixed, but they are also pretty well separated. Now, I want to show you a quick example of the if-else function so you can understand it a little better in case we come across it again. Now, this is known as a vectorized equation, this if-else statement. It's comparing each observation to this logical question. If it's true, it's going to return this. Otherwise, if it's false, it's going to return the last item in the if-else statement. So we're asking, are the numbers 1 through 5 bigger than 2? If it's not bigger than 2, it's going to return small. In this case, it returns small for 1 and 2, but then 3, 4, and 5 are all bigger than 2, so it returns the string big. Now let's go back to the code up here at the top. Instead of comparing the petals, why don't we compare the sepals? Now this you can see is a little more mixed up for the virginica and versicolor, while Setosa is still kind of off on its own. Now it's also good to analyze the covariances and correlations. So let's revisit those functions really briefly. Let's look at the correlations of the different numerical variables. So we're going to leave out the species variable because those are not numbers, and the correlation function would not work. So I'm going to ask for the correlation of the first through fourth columns of the IRIS dataset. Now let's look at a basic statistical function called the t-test. The t-test will tell us whether the means of two datasets are statistically different or not. To use it, type t.test and then put the two variables that you're interested in testing. So let's look at the IRIS sepal length versus the sepal width. We end up with a very high t-value and a very small p-value. This is telling us that the means of these two variables are statistically separate. In this lesson, I showed you a general path to follow when you first load your data. It is important to explore what the data consists of, and these descriptive statistics will give us a better idea of how to proceed. In this lesson, I'm going to introduce you to a very helpful function called the apply function. So let's load the IRIS dataset and extract only the numeric rows. So we're going to use the data function and throw in IRIS as the argument. We can look at the head to make sure we have the right one. And then we're going to pull out only the numeric variables, and we'll call it num_iris. Now here's a little problem. If we want, say, the maximum from each column, entering the max function with the numeric IRIS dataset will only return one value, and it's the maximum value from the entire dataset. Maybe there's a function like column means to get the maximum for each variable. Let's see if there's a col_max function. Nope, there really isn't. The special column functions really only exist for column means and column sums. But luckily, we have what's called an apply function. The apply function works like this. We first need to enter the data that we want to apply a function to. Then we need to specify whether we want to apply the data over rows or columns. 1 meaning rows and 2 meaning columns. And lastly, we put the function of interest, which is the fun argument, that I'm going to enter in max. And now it returns the maximum value from each variable. You can see the 7.9 from the entire dataset over here. Now, if we apply the function over rows instead of columns, it's going to return a vector as long as there are rows. Now let's try a couple other apply functions with different functions. How about range? So we can see now the max and min. Or we can try standard deviation, and this will tell us a little bit about the variance of each variable. Now this is a simple implementation of the apply family. There are other apply functions that serve other purposes. So why don't we split our IRIS dataset by species? We're going to use the split function on the IRIS dataset. We're going to split it by the IRIS species variable. So now we have a list, and the list has 3 different components. We can use a function lapply to get a summary of each component of that list. Lapply works like apply, except it applies a function to each component of list. So these are pretty nice results. You can see that lapply returns a list, which is the same length as the original input list. An apply function that is similar to lapply is called sapply. Sapply contains a Boolean argument called simplify. When set to false, sapply returns the same thing as lapply. So let's try that. Sapply. We're going to add a third argument called simplify. I set it to true first. I want to set it to false, and then you'll see it's the same as a list. When simplify is set to be true, it returns a simplified form if possible, generally in a matrix or vector form. Now, there are other apply functions, and if you want to get a list of all other specific apply functions, use the double question mark. Then we're going to specify the package to look in, the base package, followed by a double colon, and then the word apply. Let's check out our search results. And here we go. It's a list of all the different apply functions. In this lesson, we discussed the very powerful apply function. Now, there is also an apply function for time series objects, which we will discuss in a future lesson. In this lesson, we are going to be using some very popular linear models. They are easy to set up and explore and are an important tool for beginning your data analysis. Before we begin, let's load the Cars93 dataset. Let's make sure to load the mass package. And then we're going to load the Cars93 dataset using the data function. Then we're going to attach it so we can reference the variables. Now, to create a linear model, we use the LM function. The argument that we enter is the function that we are interested in exploring. First, you list the dependent variable. And for now, why don't we set the dependent variable to be weight? And we're going to set that equal to some independent variables using the tilde. We can't use the equal sign because the equal sign is an assign operator. So R would get confused if we ran into that. So generally, when we set up equations inside of a function, we use the tilde. So now let's pick some independent variables. It needs to be MPG, all capitalized. In this case, weight is the dependent variable, and we are regressing it on some variables of Cars93. Now, the simple output only gives us coefficients. We can easily extract more info, however, using the summary function. So I'm going to assign a variable, this model. And now we can use the summary function on this model, and we'll get a lot more information. So there's a lot to go over here, and soon we'll talk about how to extract specific pieces of information from a linear model. For now, let's focus on this summary output. First, it gives you the call or function that was entered into the LM function, then a summary of the residuals of the model. Each observation makes a prediction of what the weight should be, and the residual is the error between the predictions and the true weight of the vehicle. In this case, the model was off by as much as 530 pounds for one vehicle. Next, we get to look at the model coefficients, including the estimate, standard deviation of the estimate, the t-value, and the p-value associated with that t-value. Next to that, you will see 3 stars for each coefficient. These correspond to significant levels just below the coefficients. You can see it here, significant codes. 3 stars means that it is very significant and a strong predictor of the weight. Lastly, we get some more information on how the model performed overall, including the R-squared measure, adjusted R-squared, F-statistic, and p-value that all the coefficients are different from 0. Now, an R-squared or adjusted R-squared of 1 means that the independent variables perfectly explain the dependent variable. Our model comes up with 0.9, which is very good. Now let's discuss the intercept and how we can modify it using the iris dataset. So let's load it into our environment. I'm going to attach the iris dataset. Now I'm going to create a new variable called fit, which is going to be a linear model. We're going to regress petal length as a dependent variable on petal width. Plotting a linear model is very helpful. It produces 4 plots describing the model output. So why don't we set up our future plot to have 4 different panes. I'm going to expand my plot window to make sure that everything can plot okay. And now I'm going to plot the LM object, which is called fit. And we can see these 4 different plots that show up. Now when we plot the linear model, we get 4 different plots. We get a residual plot with the outliers labeled. You can see that there are 3 in this case. Observation 115, 135, and 108. There's also a normal QQ plot for the residuals, so we want the residuals to follow a normal distribution. And then lastly, there's a scale location plot, which describes how the distribution of errors change, and a leverage plot. Now you can decide whether you want to take out the intercept using +0 in the function. So if we look at a summary of the model fit, we can see that there's an intercept of 1. Sometimes you may want the model to converge to 0 at the intercept. So if you were interested in doing that, just add a +0 as one of the independent variables. And if we plot this, we might see some changes. And yes, you can see there were some changes. So making the intercept 0 is not the best for this situation. We can see that the normal QQ plot has now deviated away from the QQ line. Now let's just plot 2 of the variables as a scatter plot and add some ablines. First, I'm going to clear all my plots, so then the single plot will take up the whole window. Now we're going to add 2 different lines, one with an intercept and one without. When you use the abline function with a linear model object, it's going to produce the linear regression line. Here's the one with an intercept of 0, and if we take out that 0 intercept, we'll see it shift. Now, allowing the LM function to find an intercept will generally create a more robust and accurate model, but there are cases where you may not want to use an intercept. Now, there's also the GLM function, which stands for Generalized Linear Models. This allows us to look at other types of regressions, such as a logistic regression. And it is just as simple as the LM function, except that it requires an additional argument which tells it which variance function to use. In this lesson, we discussed how to create linear models and begin exploring the relationship between variables. It is a very powerful tool that is used frequently in the statistical world and will be useful in any analysis. Now we are going to talk about extracting information from a linear model. When we summarize a linear model, a lot of information is output into the console, but we may need to get different pieces of the model to continue exploring the data. Now let's rebuild a linear model from a previous lesson. I'm going to run this short little bit of code, which is going to load the Cars 93 dataset, attach it, and build a quick linear model. So let's look at a summary of the model. And you can see a lot of information. So now we need to know what pieces of this model can we extract. Let's use the attributes function to see how many different pieces there are to this linear model. For example, if we wanted to extract the coefficients, we would use the $ operator after the linear model object name, followed by the coefficients attribute. We can also use the COEF function, which of course stands for coefficients. This works similarly for other attributes of this linear model. For example, I can extract the residual of each observation using the $ followed by residuals, or I can use the residuals function to pull them out. Here's a simple plot of our residuals. If you want the fitted values, you can pull those out as well. Now let's create a scatter plot with weight as our x coordinates, and we'll use the fitted values as our y coordinates. And we'll use points, and we'll make the color blue. Now we can add a diagonal line using the abline function and entering in the coordinate 1, 1. So this plots an x equals y line on the graph, and it can give us a quick look at the spread of the predicted values. Generally, it is good practice to split up data into a training and a testing dataset. So let's randomly split the Cars 93 dataset into a test and training set. So for this, we're going to use the sample function, which is going to randomly pull different row numbers of the Cars 93 dataset. The size argument will tell us how big we want the sample to be. And in this case, I'm going to multiply the number of rows times 0.75. And this will return 75% of the rows. I then round that information just in case there's a decimal place. And with 93 rows, it's really hard to get 73% of that. There's most likely going to be a decimal. And we would like it to be an integer. So now we have a training index, and all I have to do is subset the Cars 93 dataset using that index. And then for the test dataset, which is 1/4 of the information, we simply have to put a minus sign in front of the training index. If you look up in our environment, you can see that we have a test dataset and a training dataset, and the training dataset is 70 observations, while the test one is 23 observations. So what we will now do is train a linear model on the trained cars dataset and apply it to test cars to predict their weights and see how well it performs. So I've attached the training dataset, so I'm going to use the same model that we first ran in the beginning of this lesson. So we can use the predict function on our model to get the predictions of our in-sample or training dataset. This is the same as the fitted values of the model. So how can we submit new data to the predict function? Let's create an object called test_predict. We're going to use the predict function, throw in our original model that we created from the training dataset, and we're going to set the argument new data to equal test cars. So we now have predictions for our out-of-sample data. So how do these predictions line up with the actual values? We'll have to go back and use the training index to line up actual and predicted values. So here, what I'm doing is I'm pulling out the weight information from our test rows. And then to get our residuals or errors, all we have to do is subtract the two. Then if we plot our errors, we can see the spread of our residuals. At one point, we were off by as much as 400 pounds. Then we can calculate the mean squared error to get an idea of how well the model performed. I was trying to square the errors first, but I forgot to write the 2. So now it should work. And let's get the mean squared error for our original training data set as well. As expected, it performed a little worse out of sample because that new information was not taken into consideration when building the model. In this lesson, we went deeper into linear regressions and how to extract specific information. We also discussed how to split up the dataset into training and testing datasets to help validate the model information and predictive power.